Now problems on one-dimensional heat equation. Heat equation. Zero boundary conditions, or boundary conditions are zero. So problems on one-dimensional heat equation with zero boundary conditions. We will discuss problems on this category. Problem number 1. Find the solution to the equation 1 by c square into dou by dou t of u is equal to dou square by dou t of u that satisfies the conditions one u of 0 comma t equal to 0 for all t, and the second condition is these are boundary conditions. One end point L comma t equal to 0 for all t, and third one initial temperature in the rod u of x comma 0 equal to x for 0 less than x less than L and L minus x for L by 2 less than x less than L. So this is heat conduction along a rod of rectangular shaped. Here we have taken along the x-axis So 0 is and the length of this rod is L. So one end is taken at origin and another end at A, that is L. So therefore here at the boundaries at 0 at L, the temperature in the rod is 0, and at a time t equal to 0 initially the temperature in the rod is given that in the two subintervals here 0 to L by 2 and L by 2 to L. In the interval 0 to L by 2, X is given. In the interval L by 2 to L, initially the temperature is in the form L minus X. Now solve this problem. That means find the solution of this one-dimensional heat equation with these boundary and initial condition. As in the previous category of one-dimensional wave equation, here also first we have to select the suitable solution. I already explained in the previous class which is the suitable solution among the three cases of solutions arises for the one-dimensional heat equation. Solution. From the given problem, we get the following conditions. The one-dimensional wave equation, heat equation is dou by dou t of u is equal to c square into dou square u by dou x square. In the problem statement also it is dou square u by dou x square, not dou t. Here in the problem previously I wrote t, but here x square. Please make a note. From the given problem, we get the following conditions, both initial and boundary conditions. First one, u of 0 comma t at one endpoint origin is equal to 0 for all t greater than 0. Condition 2, u of L comma t equal to 0 for all t greater than 0. Number 3, initial temperature distribution along the rod u of x comma 0 is equal to x for 0 less than x less than L by 2 and L minus x for L by 2 less than x less than L. This is the initial temperature distribution along the rod. Now, as explained in the previous note, write the suitable solution. First, to solve the one-dimensional heat equation. Now, the correct solution of the one-dimensional wave equation satisfying the above conditions is u of x comma t is equal to a cos px plus b sin px into e to the power of minus c square p square t. Say this is equation number 1. Now applying condition number 1 in equation 1. Condition number 1 is u of 0 comma t equal to 0 for all t. That means put x equal to 0 in equation 1. Applying condition 1 in equation number 1. We get u of 0 comma t is equal to a into cos 0 plus b into sin 0 into e to the power of minus c square p square t. Now therefore u of 0 comma t, as in condition 1, this value equal to 0. 0 is equal to a into cos 0 1 plus b into sin 0 0 into e to the power of minus c square p square into t. That means either a equal to 0 or e to the power of minus c square p square t equal to 0. Here e to the power of minus c square p square t is not equal to 0 since it is defined for all values of t. In the boundary condition u of 0 comma t is equal to 0 for all values of t. So therefore it is defined for all values of t. So it is defined for all values of t. Even for t equal to 0 also this value becomes 1 but not equal to 0, exponential value. So therefore this implies a equal to 0 since e to the power of minus c square p square t not equal to 0 as it is defined for all values of t. Since it is defined for all values of t, it will not be equal to 0. Therefore a equal to 0. Now substituting a equal to 0 in equation number 1 here. Therefore the solution becomes u of x comma t equal to b into sine px. Now substituting the value of a in equation 1. We get u of x comma t is equal to a value 0 b sine px into e to the power of minus c square p square t. Say this is equation number 2. So a equal to 0, the remaining term is b sine px into e to the power of minus c square p square t. Now applying condition 2 in equation 2. We get this is equation 2. We get now condition 2 is u of l comma t equal to 0 for all t. That means put x equal to l in equation number 2. U of l comma t equal to b into sine px into e to the power of minus c square p square into t. but u of L comma t value is equal to 0 as in condition number 2. So 0 is equal to b sin px into e to the power of minus c square p square t. This implies either b equal to 0 or sin of px equal to 0, since e to the power of minus c square p square t not equal to 0, as it is defined for all t. As explained earlier, it is defined for all t. It will not be equal to 0. Not equal to 0, since it is defined for all values of t. Therefore, either b equal to 0 or sin px is equal to 0. Therefore, now check, is b equal to 0 or sin px equal to 0. If b equal to 0, let us observe what will happen. If b equal to 0, we already have a equal to 0. A equal to 0. Then u of x comma t equal to 0. Since a equal to 0, b equal to 0, we will get 0 solution. That is a trivial solution. Here in equation 1, see, if a equal to 0, b equal to 0, this is 0. 0 into finite value, 0. So that means the temperature distribution along the rod is 0 at any point at any time. That means this is a trivial solution. That means the experiment is not going on. So at any time, at any point, if the temperature distribution along the rod is 0, means it is a trivial solution. But we require non-trivial solution. That means non-zero solution, because in the rod the temperature changes with respect to time. So therefore u of x comma t equal to 0, which is a trivial solution. So it is not possible to take b equal to 0. Therefore sin px equal to 0. Hence b not equal to 0 and sin px equal to 0. That means this is equal to sin n pi. Sin px is equal to 0 means So sin n pi value is also 0. That means sin px is equal to sin n pi, where n is an integer. Therefore, px is equal to n pi. This implies px is equal to n pi. That implies here not x, L, because we have substituted x is equal to L. We forgot to write L here. L. Here also L. Here also L. Therefore, here also L. Here L. Therefore, that implies P is equal to n pi by L. So here, in the substitution of second condition, x is equal to L. So I forgot to write L in the place of x in the right hand side. So you please make a note. PL is equal to n pi. Here P equal to n pi by L. This is P value. Substituting P in equation number 2. Substituting P in equation 2. We get u of x comma t is equal to b sin px into e to the power of minus c square pt. Put p is equal to n pi by L in equation 2. U of x comma t is equal to b into sine of n pi by L into x into e to the power of minus c square p square t. Say this is equation number 3. Since the partial differential equation heat equation is linear, the linear combination of solutions of the form 3 is also a solution. This is superposition principle. By this superposition principle, we say that the linear combination of solutions of the form 3 is also a solution. We can also write b suffix n here instead of capital B, with the n is equal to 1, 2, 3 and so on up to n. So b1 sin n pi x by l e to the power of minus c square p square t plus b2 sin n pi x by l, sorry, sin 2 pi x by l e to the power of minus c square p square t plus b2 sin b3 sin 3 pi x by l e to the power of minus c square p square t plus and so on. These are all solutions. So its linear combination is also a solution. Sum of the linear combinations is also a solution. This principle is called superposition principle. Therefore, the most general solution of equation 3 can be written as u of x comma t is equal to sigma n is equal to 1 to infinity b suffix n into sin n pi x by l into e to the power of minus c square p square t. Say this is equation number 4. Now applying condition number 3 in equation number 4. We get condition 3 is put t equal to 0, initial condition. Put t equal to 0 and then write u of x comma 0 value x for 0 to l by 2, l minus x for l by 2 to l. U of x comma 0 is equal to sigma 1 to infinity bn t equal to 0 sin n pi x by l into e to the power of minus c square p square into 0, but here p square also n square pi square by l, n square pi square by l, p square also n square pi square by n square pi square by l. N square pi square by l into 0. That means this is equal to sigma bn sin n pi x by l, and u of x comma 0 is equal to x x for 0 less than x less than L by 2 and L minus x for L by 2 less than x less than L is equal to sigma n is equal to 1 to infinity bn sin n pi x by L into e power 0 value 1. Therefore, this is exactly the half range Fourier sine series. Therefore, by using half range Fourier series, we can find the value of Bn as in the one-dimensional wave equations. Now, Bn is equal to two by L integral 0 to L f of x sine n pi x by L dx, where f of x is u of x comma 0, that is x for 0 less than x less than L by 2 and L minus x for L by 2 less than x less than L. This is f of x. This is f of x. Say this is f of x. Say this is f of x. Therefore, now substitute the value of f of x. Now, this can be written as 2 by L into integral 0 to L by 2 f of x sine n by x by L dx plus L by 2 to L f of x sine n by x by L dx. Since the function is given in the two subintervals, therefore this can be written as 2 by L into integral 0 to L by 2. This is f of x value is x into sine n pi x by L dx plus integral L by 2 to L minus x into sine n pi x by L dx. Now, integration by parts. Eilert formula, algebra first, trigonometry next by using Eilert formula. So, derivation of x and integration of sine n pi x by L. Now, derivative of x and integration of sine n pi x by L. Therefore, integration of x integration of sin n pi x by L and the derivative of x. Now derivative of x 1 and the derivative of 1 0. Integration of sin, that is minus cos n pi x by L by coefficient of x n pi by L into again integration of minus cos, that is minus sin n pi x by L by n pi by L coefficient of x. Already n pi by L is there, so therefore n square pi square by L square. Now arrow marks method we are following here to evaluate that integration. Now multiplication of these two, multiplication of these two, and multiplication of 0 into some finite value. So we are not integrating here because 0 into that value is equal to 0. So that's why we are not integrating further. Now therefore here alternatively plus minus plus, alternatively plus minus plus. Therefore again same integration of L minus x into sin n pi x by L, same integration. Instead of x there we will get L minus x, and derivative of L minus x is minus 1 and derivative of minus 1 is 0. Derivative of L minus x, integration of sin n by x by L, L minus x sin n by x by L. So L minus x derivative is minus 1 and it is 0. Again its derivative. So here same minus cos n by x by L by n pi by L, and again minus sin n by x by L by n square pi square by L square. Arrow marks alternatively plus and minus. Multiplication of these two, multiplication of these two, multiplication of 0 and a finite value that becomes 0. Here plus sign, minus sign, plus sign, alternatively plus and minus. Therefore this is the integration of a second integrand. Now write down these integrations and substitute in the above equation here. Now Bn is equal to 2 by L minus x into cos of n pi x by L by n pi by L minus into minus plus sin n pi x by L by n square pi square by L square. Limits 0 to L by 2. Plus minus L minus x into cos n pi x by L by n pi by L, minus into minus into minus, minus sin n pi x by L by n square pi square by L square, minus L minus x into cos of n pi x by L by n pi by L. Again, next term, minus into minus into minus, sin n pi x by L by n square pi square by L square, minus sin n pi x by L by n square pi square by L square. Limits L by 2 to L, L by 2 to L. Now simplify. This is equal to 2 by L, upper limit L by 2 minus L by 2 into cos of n pi by L into x value L by 2 by n pi by L, minus lower limit minus of minus plus 0 into cos 0 1, 0 into 1, 0 by n pi by L. So therefore plus 0. Next, here upper limit sin n pi by L into L by 2 by n square pi square by L square, minus lower limit sin of 0, 0. So therefore sin n pi by L into L by 2 by n square pi square by L square, second term is 0, plus sin of n pi by L into L by 2 by n square pi square by L square. Therefore this is the first part. Next, plus into minus, minus L minus x, upper limit L, L minus L, 0, cos of 0 1, 0 into 1, 0. Therefore this term becomes a minus 0, and lower limit minus of minus plus L minus L by 2, L minus L by 2, L by 2 into cos n pi by L into L by 2 by n pi by L. L by 2 into cos of n pi by L into L by 2 by n pi by L. Again here minus upper limit sin n pi by L into L by n square pi square by L square. Lower limit minus of minus plus sin n pi by L into L by 2 by n square pi square by L square minus sin n pi by L into L by n square pi square by L square minus of minus plus sin n pi by L into L by 2 by n square pi square by L square. Therefore now simplification, further simplification, L gets cancelled. Here also LL gets cancelled. LL gets cancelled. LL gets cancelled. LL gets cancelled. Therefore here minus n L by 2 cos n pi by 2 n pi by L. Here also L by 2 cos n pi by 2 by n pi by L. So this is negative quantity, this is positive quantity. These two quantities gets cancelled. So therefore these two gets cancelled. Now here sin n pi, this value becomes 0. Therefore these two values are remaining quantities. Therefore this is 2 times sin n pi by 2 by n square pi square by L square. This is equal to 2 by L into 2 times reciprocal of this one, L square by n square pi square into sin of n pi by 2. So therefore this is equal to, now here LL gets cancelled. L. Therefore 4 times L by n square pi square sin n pi by 2. This is a Bn value. Bn is equal to 4 times L by n square pi square into sin of n pi by 2. This is a Bn. Now substituting Bn in the most general solution, equation number 4. So substitute the value of Bn here. Substituting the value of Bn in equation 3. We get u of x comma t is equal to 4 is a constant, L is a constant, by pi square is a constant, sigma n is equal to 1 to infinity, Bn value sin n pi by 2 by n square into sin of n pi x by L into e to the power of minus c square n square pi square by L square into t. This is our required solution for the one-dimensional heat equation with the given boundary and initial conditions. Second one, homework. Solve the equation. Dou by dou t of u equal to c square into dou square by dou x square of u subject to the condition to the boundary conditions u of 0 comma t equal to 0, u of L comma t equal to 0 for all t greater than 0, and initial condition, initial temperature in the rod at a time t equal to 0 at any point is equal to x for all x. That means temperature distribution in the rod as x at a time t equal to 0. If x value is 0, then it is 0. X value is 1.2, it is 1.2. X value is 5, it is 5. 6, it is 6 degrees. So this is the temperature distribution. Solution is the same as in the problem number 1. Up to equation number 4, there is no change in the solution. You just copy the solution from beginning to till equation number 4 with a simple modification. Instead of u of x comma 0, there another condition is there, another function is there, but here x, you just replace that one and continue the remaining solution till equation number 4. After that, apply condition number 3 and then find the value of Bn. This is the homework problem.